2 to the 30 work to get all of the second block conditions satisfied. Okay? Is 2 to the 37 a big number or a small number? I ask a room of computer scientists. A number theorist would say everything's infinitesimally small that you write down, right? If an inner loop is somewhat simple, can you run 2 to the 37 iterations on a computer in 2006? Yeah, it's well within the range of what you can do. Okay, so using an IBM 690 computer, which is a very powerful computer, not what you're going to find in my laptop here, it took an hour, about an hour, to get the first block found. In other words, to satisfy those last 37 conditions. And then for the second one, only 2 to the 30 work is needed, so that's 128 times simpler. About 15 seconds to 5 minutes to find suitable M2. So in a little over an hour, she can find collisions this way. Okay, satisfying all those, most of the conditions deterministically, and then flipping bits for a while until the rest of the conditions are satisfied. I'm leaving out a lot of details here, but okay. Since then, people have been working on follow-up research related to Wang's attack. The first to produce anything was a guy named Vlastimil Klima, and he improved the attack down to 2 to the 33 for the first block, 2 to the 24 for the second block. And then I, with a couple of students last year, which just appeared last month in FSC, got the first block down to 2 to the 30, and we also implemented the attacks. So if you wish, you can go to my webpage and you can actually download the MD5 toolkit, which is supposed to be a platform for doing further research, testing. You can generate your own collisions yourself, and believe me, it is great fun. So you should definitely try it. Also, there is a full version of the paper, which you can find also on my website, that goes on for 39 pages about all these details that I've left out, because that's also great fun. Okay. The latest things, this is a very fast-moving area, as you might expect. Since we published our results just last month, 2 other groups are now coming up with even faster implementations. The 2 typical ways to get things to go faster: 1, improve the algorithm, and 2, throw hardware at it. So HashClash is a project in the Netherlands right now that throws hardware at the problem. They use highly parallelized attacks because these things are very parallel. Those 2 to the 37 trials, you can run them all at the same time if you have 2 to the 37 computers, or appropriately proportioned. This project, they've generated millions of MD5 collisions. They start generating them to order, like if you have a specific first block you'd really prefer, then using birthday phenomena can generate this chosen second block, a random second block. And then Klima has now come up with a new technique he calls tunneling. I haven't looked at yet, but he claims that it is much, much faster, and he has an implementation that runs in 17 seconds. That was posted to a mailing list last night at 1 o'clock in the morning, so fresh off the presses. Both groups are saying they can produce collisions in less than a minute now. So that's, we were at 5 minutes, and they're now much faster. But like I said, all of the research really has been focused on just speeding up the existing attack by adding conditions, but not by understanding differential. Okay, so what does all this mean? MD5, you can now find garbage 1 and garbage 2, and they hash to the same thing. Is it time to throw MD5 out? Does that lead to anything interesting? Does that lead to attacks? One thing I can't do is I can't take a contract that you've signed that was signed using MD5 and come up with another contract that says you promised to be my personal butler for 5 years and get the hash to collide there so it looks like you signed the different document. We don't know how to do that. That was our second preimage resistance. All we can do is get 2 blocks of garbage to collide. Can we do anything with that kind of an attack? I mean, it's definitely of theoretical interest, and it adds fuel to the fire of those who say that MD5 should be retired. All right, so there are some kind of tricks you can pull in order to get things to collide in an interesting way, and they are tricks, and I'll explain why in a minute. So here's a result from our paper from last month. We can make 2 distinct Linux binaries collide. So here they are. I run a program called B1, binary 1. It says hello world. B2, you run it, it says erasing your hard disk, please wait. Okay, so these are definitely different binaries because you run them in the same environment twice and you get 2 different results. And here's the MD5 of B1 and B2. They're exactly the same hash. How can you do that? It doesn't seem like it should follow immediately from the collision we just discussed, which was just 2 blocks of garbage. Okay, well, it's using a trick. So if you know what binaries look like on Linux or ELF or almost any platform, they typically start out with a text segment, which is the program code, and then have a data segment. And here the data segment is different. In the data segment, there's a 1024-bit chunk that is distinct within those two. And in fact, they're distinct in exactly 6 bits, our usual friends, those 6 bits that matter for an MD5 collision. And they're generated using the proper chaining value if you hash the program down to that point. And then it's an MD5 collision carefully placed into the data segment. Okay? Everybody with me? Okay. So these two things will hash to the same value. But now why do they run differently? Anybody want to take a guess how you could get B1 to run different from B2 now that you've got these two programs?
Because the CD doesn't matter, right?
The chaining value doesn't matter. You can find a collision for any. So we actually, when you do this attack, you actually have to compute the chaining value down to the start of where the collision is, generate a collision for that chaining value, and then plug them in.
You can do anything you want.
What do you mean you can do anything you want?
Well, you can do a lot more than using the chaining value being the same. That's crucial, right? Not having to be the same.
You can have one program that looks at 1 bit in the data and then does
behaves differently.
One thing or the other.
That's
thing.
it. That's exactly it. So the program, because it executes, can actually look at the data segment and say, let's look at the 19th byte, the high bit. And it happens that the 19th byte will vary in an MD5 collision. And you say, well, if the high bit's set, say hello world. Otherwise, say erasing your hard disk. So behave differently depending on if you're in the binary 1 where there's a certain the first piece of garbage, or in binary 2 with the second piece of garbage. You can follow that. You just look at yourself and behave differently based on which version you are. But yet the two binaries will have the same hash value. So the reason that this is ridiculous in some way is because if you tried to pull this, well, let's do the next example, which is more interesting and uses the same trick. This is by Marcus Daum and Stefan Lux, and they use the same technique, and it's their technique. So they did it first. I should make that clear. They had 2 PostScript documents that collide. That's a bit more interesting, right? You look at one document, and it says one thing. It says, I don't know, I pledge to pay $500 a month in rent. The other one says, I'll be your butler for a year. And it looks like you've signed one when actually they're claiming you signed the other. And here it works the same way as the previous example. It turns out PostScript is a programming language. Did you know that? PostScript actually is a programming language. So you can do the same exact thing. You embed a collision somewhere in a PostScript document, and then using the PostScript programming language, you see which document you are. If you're in the first case, you output, I promise to pay my rent. In the second case, I promise to be John's butler. Okay? So now you sign the first one that says you'll pay your rent, and then I go take you to court and say, look, you're supposed to be my butler. It's right here, and I've got a digital signature, and it's all good. Why is this fishy? Why would this not hold up in court? Yeah. You look at the PostScript source, and you say, wait, there are 2 different documents embedded in here and a program that's selecting one based on some weird bit down lower, right? That's pretty fishy, and I think that anybody with the amount of technical sophistication, especially knowing of this attack, would immediately say, you've been duped, and you clearly signed one version or the other of this document, but we're not going to claim it was one or the other because it could have been either one. Nonetheless, this is kind of an interesting trick, and people thought it was quite amusing and maybe even important. Another example is Lenstra and De Weger showed that you can get 2 X509 certificates to collide. Basically, they put an MD5 collision in the first 1024 bits of the modulus, and then randomly generate the last one so that they get a proper RSA modulus that differs in those 6 bits. It turns out you can generate 2 moduli that differ in specified bit positions, and this is a known result from a couple of years